In this part, we're going to look at stack trace obfuscation. We're going to look at or examine what that is, talk about how that's used or why it's used, and then we're going to look into some POCs of it ourselves, as well as finding the techniques ourselves. Um, there's some public materials, on GitHub and that out there on some of these techniques. So the main point I want to kind of instill as we look into this is not, how do we just convert public code in C to a Rust POC, but rather how we go about finding these techniques in the first place, and then looking into developing a POC for it. One method will be using a publicly known one. Another one is, well, at least I have not found it publicly yet. So whether it's out there and I just didn't find it or not, who knows? But it was a pretty easy find, and I'm not even sure if it's going to work, but we're going to try it. And that's part of the experience, right? So I have a Procmon trace here. These are both load image events, um, and it's from the same process, and it's just loading a DLL, uh, two different DLLs. But when you look at the stack trace, the one on the left-hand side is valid, right? You see at the top here when it gets into the kernel and it got captured, and that came from anti-DLL. But like the first call into a system DLL, like anti-DLL or kernel base, from a non, I guess, like system DLL, was at this point, right? Where somewhere in on frame 27 here, Windows storage.dll at some location, some offset in there, made a call that went to NTDLL. And NTDLL eventually went down to loader resolve delay loaded API. And then that goes all the way down, and that starts loading in a DLL. You can see the entire stack here, the start of the thread, initialization of the thread running in Microsoft Edge update, that going to Windows Storage DLL, and then that doing something that triggers a delay loaded event in NTDLL to load a DLL. And on the right hand side, we have a stack trace of this DLL load, but you see that it doesn't have a module name. It's marked as unknown. So there was definitely addresses that were, like, this code was all being executed, but um, it can't tell us what the name is. And then it goes to some other DLL, and then it's got some more unknowns. So it resolved the stack trace. Like, it still found the stack frames and everything. It just doesn't have a module name. And the reason why I show these is on the right-hand side, what module actually triggered the DLL load, it's hard to say. We have the IPHL PAPI one, but we don't know if that was responsible for triggering the DLL load, or if that went to some other module that then triggered the DLL load. And the reason why this is a relatively important distinction is because some EDR products or AVs or whatnot, when you try to do certain things like load a DLL, they may actually consider the stack trace, and they may unwind the stack to try and find which module in the process is trying to do that operation, trying to load a DLL or something. And the reason why that's interesting is if it's coming from a signed proper module like Windows.storage.dll here, it might permit it. But if it's coming from just some random address that's not even mapped to a module, where it can't actually reference the module name, it might block it. And there's a few reasons for that. One is like shellcode execution. Think about running Dynamics shellcode, whether you exploited, whether you got like remote code execution on a system because you did like a use after free style attack and you got your shellcode running from the heap. Or if you did a Stack Overflow and you're actually directly executing code from the stack for whatever reason. In those cases, the code that you're executing is a shell code that's been allocated in a buffer that's not part of a module's address space, right? You're not in like the text section of a valid PE format module. You're in a heap buffer or a stack buffer or something like that, and you're making calls to like load a DLL from that place. It's the same as if I created a buffer with some shellcode and just ran it, right? Or if I did virtual alloc in a different process, placed my shellcode there, marked it executable, and started running it, which is a very common way of doing like process injection. You would use virtual alloc to allocate a buffer in the target, mark it, you would write your shellcode to it, mark it executable, and then spawn a thread in there. In that case, that code that's running, it doesn't belong to any module. It's running from a heap allocated buffer. So you wouldn't have an associated like module name with it. It would just be like unknown, like here, and have a address that's pointing to the heap. Now, when you do that, if an EDR intercepts your DLL, load DLL call or something, it might see that you're running from a dynamically allocated buffer like a heap address and block you. Now, of course, it's not going to do that it'll probably not do that for every process, because some processes like browsers and that typically use JITs, which may do that, which may be what we're seeing here actually. I'm not sure, but there are some cases where it will block on that. So sometimes it's also an obfuscation thing. If you can say that when you do a DLL load, that the stack trace doesn't show your module or anything at all, it just shows like legit modules that like NTDLL and that's it, then that looks clean, and it also kind of hides what you're doing a little bit more. So there's kind of twofold. The main reason is to look legit for EDRs, but the second one is to kind of hide what's actually happening from, a reverse engineer or something. So that's what we're going to play with. And there's a few ways you can do this. One is just say you want to do something, right? Like load a DLL. Instead of loading it yourself, you get someone else or something else to load it for you. In which case, when they do it, the stack trace will point at them, not at us, right? And that's something like this, right? Say we have our own process. We have NTDLL, we have kernel base, we have our proc, and we want to call load library on some DLL. If we can get something else, some other part of Windows or something else to call load library with our provided argument for us, then that's mission accomplished, right? We didn't do it, so we won't show up on the stack trace. Some other process or some other thread or some other code did it for us. And this means that we need to look for ways to pass a function pointer and an argument to something such that it will call it. Now, there's a few mechanisms in Windows for that. And you can find them by searching for certain keywords. So a lot of these keywords relate to things like callback, right? What's a callback? Well, a callback is really a mechanism where I provide something, a function pointer usually, and then when some condition happens, that thing will call the function that I provided it. Now, normally you would provide it, the function based on whatever you're trying to get a callback for. But there's nothing stopping me from just inserting an arbitrary function pointer there, right? Another one is like work items or like queue, because some things you don't want to process right away. You want to process it asynchronously. So there's normally mechanisms in an OS to queue something or create a work item where you describe the task by perhaps giving it a function pointer and arguments, and that goes in some queue somewhere. And then somewhere down the road, that queue will be processed by something, by some thread, and executed. The Windows kernel has these, APCs. We have them. There's a few ways of doing this. But by knowing these keywords, we can take these keywords and we can search the SDK header files for these keywords. I've got even, just NTDLL loaded here. And if I start searching for queue, I've got drain work queue. Now, drain work queue usually means that it's processing the work queue. It's going to pop off an item from the work queue one by one, probably in this while loop, and it's going to do whatever the task is. It's going to execute the work, process work, and, handle it. We have RTL queue work item, which is interesting. Now, if I look at RTL queue work item, we have XQ work item, but this is in WDM.h, which is, this is a kernel thing. That's not what we're after. We want to look at the user NTDLL RTL queue work item just because it sounds interesting and I want to know more about it. There's no RTL queue work item that's publicly documented properly from Microsoft. You see that there are references to it though in NT API crate. There's references up here in Wine, and things like that. But there's, this is a publicly known method actually. So you'll see that there'll be some posts from other people on it. But what if we wanted to figure out more about it without, looking at public materials that's not official? Well, there's other ways we can find this, right? RTLQ work item, it's not referenced anywhere else in NTDLL, but it is a valid exported function. So what if I search other DLLs on my system for imports of this function and see what they do, and maybe they're documented? So if I grab RTLQ work item, and I open up kernel base here, kernel base, right, is interacts a lot with NTDLL. In fact, I think it might just import into DLL. Let me quickly check. Okay, NTDLL and some, Win32 DLLs as well. But it does interact closely with NTDLL. So what if I search for RTLQ work item? You'll see that kernel base imports it. Now I just need to find cross references to it. I can see that there's a cross reference to it in QUser work item. QUser work item is a exported function from kernel base, and all it does is call RTLQ work item, essentially. There's some other things, but that all happens after this. So it's literally whatever parameters you pass to QUser work item are going to be the same parameters you pass to RTLQ work item, because QUser work item just forwards on to RTLQ work item. So now I can search for QUser work item instead and see if that is documented. And you'll see, yes, there is QUser work item documented on Microsoft officially. So I can look at the official documentation as to what QUser work item or RTLQ work item takes. You can see the first parameter is a function. The second parameter is a value that's going to be passed to that function. And then the third parameter is just a flag that can control a few things. And that's it. Since we can pass it a function and it says it's going to queue it to a worker thread in the thread pool. So it seems like the system has a few worker threads in a designated thread pool, and you queue this work item, and then at some point, it'll be executed and ran by a thread in the thread pool, which should not be our current thread that calls this function. Meaning it's going to be executed by some system thread, probably, and the call stack is going to look something like, probably starts from like NTDLL and then just jumps straight to the function or something, right? It's not going to really be associated with our module. So this is one method of executing a function without the call stack of it being traced back to our location, whether we're running it from a heap buffer or just a module we want to hide. And this one's, there's public POCs of this. But one that I haven't seen a POC for yet also utilizes callbacks. All I need to do for that, right, is look for other keywords, right? Callback. There's a few here. Let me search NTDLL as well. There's a few, but there's more than just NTDLL and kernel base, right? I could search the entire SDK um, header files for the word callback. I can also just, what if I just search MSDN here for underscore callback? Since a lot of types are um, marked underscore callback in caps. Well, there's a few callbacks, right? There's a callback in the storage engine, stuff here, WS callback, CF callback, PD callbacks. If I filter this down, I'll search Windows NT. Got TP callbacks and stuff. Okay. What else is under Windows? And what if I just search all of Windows here? Shell callbacks. There's like quite a lot of potentials here that would work. Um, but the one that I specifically wanted to give a go off is this one, mini dump callback routine. Because we wrote our own like custom mini dumper, but we haven't used the official like mini dump write dump function before. But this is commonly used as well in like malware and stuff to just create a to just write a mini dump. And you'll see that one of the parameters to the mini dump is a pointer to a callback information, mini dump callback information. And you'll see that that is actually this structure contains a callback routine, which is a function. And then it takes a parameter, which is just one parameter that's going to go into that function. You'll see that the definition of the callback is takes 3 parameters and returns a Boolean. Now we want to call load library, right? Load library A. Let's say load library A. That returns a H module and takes a 1 parameter. And that's its definition. So what if we wanted to have load library A be the callback that we pass in when we write a mini dump so that we actually get a call stack that doesn't belong to us? How would that look? Well, this is expecting a bool, but actually a bool in Windows is not just 0 and 1. It's actually supposed to be like true is defined as 1, false is defined as 0. But part of the Microsoft recommended coding style is that any non-zero value, so any value greater than 0, is true. So you're not supposed to check whether the return result directly equals to true. You're supposed to check whether it does not equal to false, because a bool value of 6 would actually be considered true. Now, this isn't using just the BOL. This is like capital BOL, Windows' own bool type. Wonder if I can find more documentation of that. Check if true MSDN. Maybe here will show more about that. This is .NET. Really want to look at C. MSDN, bool type, C. I know I had a page earlier. Maybe this one? So it's an int, right? It's a 32-bit field. Now it does say 1 indicates true, 0 indicates false, but there is somewhere where it specifically specifies that it can be any non-zero type is valid as true. Uh, this is Reddit, but it probably says the same thing. Um, Where is it? Bool. See, for example, the return type here is bool, and it'll return false. But if it's true, it will return file attribute directory casted to a bool. File attribute directory is is 0x10, right? File attribute directory is 0x10, and that function before here will return that, but casted to a bool. So if it's true, it's actually going to return 0x10, right? 0x10, that's not 1, which is why I can't find it. There is somewhere on Microsoft about the coding style of bool, but what you're supposed to do with bools is check if it equals to false or doesn't equal to false, because any greater than 0 value is considered true with the bool type here in Windows. And load library A returns H module, which is only going to be greater than 0 when this call succeeds. When this call fails, it returns 0. So this can actually act as a bool. It may get truncated to a 32-bit value, but that doesn't matter. For the purposes of this needing a bool as a return value, it will work. And the other thing is this takes 3 parameters, this takes 1. However, we're working with 64-bit systems here. We're not running this on a 32-bit OS or from a 32-bit process. So these parameters, which are both 64-bit in size because they're all pointers, are just going to be RCX, RDX, and R8. So it doesn't matter if there's 3 parameters or just 1. Those 3 parameters, those 3 registers are expected to be clobbered regardless. So they won't actually interfere with anything, though they shouldn't. We should be able to call load library A with 1 parameter, and even if it's expecting to pass 3, it doesn't matter. So we're going to give that a try as well. So there's 2 parts to this, right? One is call mini dump write dump. Now, we're not calling this to actually execute it or like dump LSAS or anything. So you can just dump your own process. Just pass in your own process handle. It doesn't matter. The whole purpose of us calling this is to just see if we can provide a callback that points to load library A to load a DLL of our choosing and see if that actually works or not. I haven't tested this, so I'll be doing this, testing this as well as I walk through the solution. But it's a example of just finding a callback and giving it a try and see what the stack looks like. So when you do run that, pass through a DLL that's not typically loaded by your process, and then spawn up a procmon trace. And in your procmon trace, you can add in a filter where the operation is load image, load space image. And you can even do where path is and then provide the path. Maybe you're loading C drive, Windows, System32, some random DLL.dll, right? And you filter on that and run your code, and you should be able to see the procmon load image event for the DLL that you're loading. And then view the stack trace and see what it looks like. See if it goes to your process or something like that. The second part to this is using QUserWorkItem to do it. We provide the function, the parameter, and the right flags, run this, and then capture the procmon trace as well. And compare the 2 approaches. Compare the procmon trace from QUserWorkItem to minidump callback routine. And maybe there's some maybe there's some concerns with using mini dump write dump. Maybe it does load the DLL, but then after it loads it, something goes wrong with the mini dump and it crashes. Don't know. We'll give it a try and we'll take it from there.